Good morning to all. I am Moorthi Lokanathan. Today we are discuss about the ordered Pt2 Fe nickel ternary nanocatalyst for oxygen reduction reaction in polymer or hydrogen fuel cells. Here in the introduction, our everyday life we are using energy sources as fossil fuels such as petrol, diesel, gasoline, etc. So, but this is exhaust and limitation of the thermodynamic system. So, we need alternate energy source. There are several alternate energy sources such as fuel cells, batteries, wind energy, etc. Among various energy sources, polymer electrolyte membrane fuel cells or hydrogen fuel cells creating higher attention due to its high efficiency, eco-friendly and higher power density. So the problem in the hydrogen fuel cell is sluggish kinetics reaction of the oxygen. So we want to improve the kinetics of the oxygen reaction. So we need more catalyst. So the variety catalyst available: noble metal free, metal free catalyst. Among all elements, platinum only giving more activity with respect to the oxygen binding energy. So we are only focus the platinum based catalyst. If we are using bare platinum, it is high cost and low availability. So we need increase the activity as well as reduce the PT content. So we are making PT with the low cost transition metal alloys. In these studies, we are preparing platinum with Fe nickel ternary alloy electrocatalyst through simple solid state impregnation method followed by heat treatment under reducing atmosphere. Finally, we are getting ordered FCT alloy with L10 phase. After the preparation of the catalyst, we analyze the X-ray diffraction pattern. Here we compare three X-ray diffraction pattern. The black line corresponds to the commercial PTC, bare PT. The red line corresponds to the Fe nickel PT with inert atmosphere, no reducing condition. The blue line under reducing condition. So compared to other both, the blue catalyst, our Fe nickel PT H named catalyst having superlattice peaks such as 001, 110. This is correspond to the ordered structure. Now I can explain. We consider our single unit cell of the FCC phase centered cubic structure. Here only the particular layer of the atom of PT replaced with nickel or Fe transition metals. What will happen? The atomic size will be reduced. So the atom distance between PT to PT will be reduced. So the C distance will be decreased. So the C by A ratio become less than 1. So this is correspond to L10 phase, means ordered structure. Then we employed the microscopic analysis. From the microscopic analysis, we find out that the individual nanoparticle deposited on the carbon support with the formation of the majority nanoparticle with the size is 6.4 nanometers. Further, high resolution temp microscopic images confirm the presence of the d-spacing. The value is 0.2 to 3 nanometer. This is correspond to triple facets. So the nanoparticle having triple facets surfaces on their outer layer. From XPS, it's confirmed presence of the PT, Fe, nickel and carbon support in the catalyst as well as the compared to bare PT The PT based alloy having high binding energy shift almost 0.25 electron volt in the positive direction. This is due to the hybridization, means the Fe and nickel 3D to PT 5D hybridization. In that case, what will happen? It will increase the PT electronic 5D vacancy. So it's influence the PT electronic structure. The increment of the 5D vacancy is highly boosting the oxygen reduction reaction. Now let's see the electrochemical characterizations. First of all, we discuss about the single and half fuel cells. A single hydrogen fuel cell consists with anode cathode in between polymer electrolyte membrane. We calling as a MEA, membrane electrode assembly. Here at our research work is only focused on the cathode oxygen reaction activity. So the same cathode oxygen reaction activity will be cathode reaction mimic in a 3 electrode system, because a single fuel cell testing is high cost. So we won't do the same measurement in a lower cost measurements. So we are approaching a 3 electrode system. Here our catalyst coated on the working electrode as a modified working electrode, but the modified working electrode will be monitored with the respect to the reference electrode and counter electrode. We are using two type of modified electrode. One is reverse rotating ring disc electrode and this rotating disc electrode. From this we are measuring the cyclic voltammetry. From the cyclic voltammetry, the hydrogen desorption or absorption region, we calculate the area under the curve. This is correspond to the electrochemically active surface area. Then we running the linear sweeping voltammogram. From the linear sweeping voltammogram, we calculate the kinetic current with help of the Cauchy-Lewis equations. From the kinetic current, we are calculate the mass and specific activity. So from the calculated activity represented in the bar diagram, the before and after 10,000 cycling, there is no activity loss after 10,000 cycle, only negligible activity only happening. So from this we conclude this catalyst is highly stable in acidic condition even after 10,000 potential cycles. Here we are indicating few phenomena, the reason for the activity loss during the cycling, namely Ostwald ripening, particle detachment, atom dissolution, particle agglomeration and carbon sulfate corrosion. These are the reason for the activity loss of the catalyst during the potential cycling or the stability cycling. So now we can conclude. We have successfully prepared the FeNiPt ternary electrocatalyst through simple solid method under reducing condition. The ordered FCT structure confirmed through the X-ray analysis with help of the superlattice, the presence of the superlattice peaks. The higher electrical activity due to the preparation of the reduced atmospheric condition, as well as the influence of the transition metal on PT electronic structure, means deep bond downshift. Acknowledgement. The author acknowledged the FeNiPt 2021 project number 3200113 FeNiPt INIT, Republic of Chile, for the financial support. Thanks for your kind attention.